Welcome. This is lecture 56, and in this we go back to our Grosvenor basis things, and then we'll see, we saw how it could be used to compute syzygies for an ideal. So this is mostly an overview of things that we will not prove, but at least to discuss how one could use this to compute a free resolution, okay? Not just the syzygy of an ideal. Okay? So really, when I meant here at this point, when I meant syzygies, I mean we do mean free resolution, all of them. Syzygies, then the syzygies of them, and so on. Okay. So in an earlier lecture, we saw how a Grosvenor basis was used to construct syzygies. Okay. The same thing can be carried over to of an ideal, and so far we only looked at computing Grosvenor basis for ideals, but it can actually be generalized to not all modules, but submodules of free modules. So how is that done? So remember, an ideal itself, ideal also is a submodule of a free module. It is a submodule of a free module of rank 1. Okay. So that's, and again, this would be finitely generated, at least for us. We will not worry about arbitrary. Okay. Okay. So I'll just briefly give an overview of how this can be done. Okay. It is essentially just rewriting everything that we did for ideals in terms of modules. So it's also a good way for us to recap how, one proceeded with ideals. Okay. So let F be a free module with a given basis of rank R. Okay. So E1 to ER basis. Okay. By a monomial of F, by a monomial in F, okay, we mean an element of the form okay, a monomial in R times a basis element. For some A1 through AN non-negative, okay, all of them non-negative, and 1 less than I less than R. Okay. So this is what we mean by a monomial in F. Okay. So it's exactly like a monomial ideal. It's exactly like a monomial in S, in the polynomial ring R. Okay. It is just okay. A monomial submodule of F is a submodule generated by monomials of F. Okay. Now, if we have a monomial submodule, then generators would be of this kind. Okay. Let's collect all the generators with a fixed EI. Okay. If you multiply them by elements of R, we would get all R linear combinations of these monomials. In other words, we will get a monomial ideal. Just the coefficient, if you just look at all elements in the monomial submodule, okay, which involves only one term, okay, EI, and these then and arbitrary R linear combinations. So we would just get some element in a monomial ideal times EI. Okay. That's the first observation. So I'll write them, but let me finish the. Secondly, if we have some, so therefore, so let M be a monomial submodule. Okay, so I'm just writing down what I just said. Then Mi, which we define to be, okay, all elements of the form R times EI. R times EI is inside M. So all elements in M that are of the form R times R is in R. Okay. But a fixed I is, of course, it's a submodule of M, and is of the form I times EI for some monomial ideal II inside R. Okay, that is because we take a generating set in which a generating set for M which involves monomials. We fix a monomial generating set for M, and in that pick out all the ones that have this EI, and then our linear combinations would just be combinations of that. Okay, so this is the first observation that we want to make. Secondly, Mi intersect Mj is 0 for all I different from j. That's clear because all of these are multiples of Ei, all of these are multiples of Ej, and they cannot have an intersection. And thirdly, M is M1 plus M2 plus up to Mn. Okay, and this now says that M is the direct sum of these Mi. Sorry, not N, R. There are okay. So in other words, conversely, if M is a direct sum of such things, then M is a monomial submodule. So a monomial submodule is, so M inside F is a monomial submodule if and only if there exist I1 through IR monomial ideals in R such that M is equal to I1 E1. I1 E1 is a submodule of F, and the direct sum IR ER. Each of them is a submodule of the corresponding factor inside here, and then the direct sum of that is M. Okay, so this is what we just wanted to observe. So now we can define a monomial order. We can define monomial order on F analogous to R. How it's done on R, meaning we have to give a total order on the set of monomials that respects multiplication. Okay, so that's okay. So total order on the set of monomials that respects multiplication. Multiplication by, so these are monomials in F. So these are monomials of F that respects multiplication by monomials of and these are monomials of R. Okay. So by the way, I should have stated this. This description in this generality is there in Eisenberg's book. Eisenberg's, one of the references that I had given. Okay. Not every book discusses this in that generality, but that discussing it for ideals is not enough to describe how syzygies will be, how a free resolution would be computed. Okay. So then we have an analog of Buchberger theorem, S polynomial, I mean all those things, analog of Buchberger theorem. So let's briefly review how that is. Okay. So F as above, and let G1 through Gt be in F non-zero elements. Okay. For I different from J, okay, for I different from J, define Mij to be the LCM of the initial term of Gi, initial term of Gj divided by initial term of Gi. Okay. So the Mij, the denominator is, this is symmetric in Ij, the denominator has just Gi. Okay. So this is, okay. And for each, so then division algorithm. I mean, not division algorithm, but the consequence. So there's a division algorithm in this context. Division algorithm gives, okay, Mij Gi minus Mji Gj. So this is the S polynomial. This would be the analog of the S polynomial in the ideal case. This is of the form some q u, of course this depends on I and j, times gu. So we are expressing the S polynomial in terms of the other, I mean in terms of the generators, not necessarily other generators, but the generators, plus some Rij. Okay. And again we have seen this Rij need not be unique, but one can ensure that no term of Rij is divisible by the initial term of any Gu. Okay. So with no term of Rij divisible by in Gu for any u. Okay. So we can this is just the same thing that we did for modules, for ideals. So we can write it like this, and then the Buchberger criterion is, so yeah, so we are, okay, Buchberger criterion, the theorem, okay, that, I mean Buchberger's theorem was for ideals, but it can be generalized like this. G1 through Gt is a Grobner basis okay, for the submodule of F that it generates, for the submodule generated by it, okay, if and only if Rij is 0 for all I different from J. Same, we compute this, and it becomes a Grobner basis exactly when this remainder is 0, and if the remainder is, so the algorithm is, we compute this, the remainder is non-zero, then add that also to the list of to the set G, and then we redo all the calculation once more, and then if the remainder is then we check if there is any leftover remainders, and then we add, and so on. Okay. So and what does this mean? I mean, what does it mean? Grobner basis for the submodule. So it means exactly what it had meant earlier, that that is in of Gi this set 1 less than or equal to I less than or equal to T generates generates the submodule generated by generates the submodule of F generated by the initial terms of all the elements in M. Okay, so exactly analogous to what we do for ideals, one can prove the statement. Okay, and we will okay, so we will not attempt proving it. So this is now the key point in this approach. So this is just describing how to compute. So now we have constructed. So now we have constructed a Grosvenor basis for M. Okay, and then it means that. Okay, so therefore, for all I different from J, so let's say this Grosvenor basis is G1 through GT. Okay, so just call again G1 through GT. Then for all I different from J, we have this Mij Gi minus Mji Gj equals some coefficients Gu, and the remainders are 0. That's precisely when it's a Grosvenor basis. So this gives us syzygy. Right? This can be rewritten as a relation. Okay, so this gives a syzygy. Okay, and the theorem is that all syzygies are generated like this. So this tells us what is the kernel of the presentation matrix is, not the presentation, the surjection is. Okay, and then from that we can construct a presentation matrix and so on. Okay, and so we can proceed. Okay, so repeatedly. Okay, so this is the idea. So now, okay, so repeat this for the kernel of. So remember, M is inside F. Okay, some F1 surjects onto this, because we can choose a Grosvenor basis like this, and then we know what the we'll get a surjective map, and then we repeat this for the kernel of this map. Okay, so let's just call this thing epsilon. Repeat this for the kernel of epsilon. Epsilon is this map. Okay. So I mean, this thing tells us the kernel of epsilon, and then repeat the same compute a Grosvenor basis and so on, and then repeat this, and that would give us a free resolution. Okay. Now, in theory, this will also prove Hilbert's syzygy theorem. Okay. But we need a technical statement for that. So, in principle, this will prove. I mean, one can prove Hilbert's syzygy theorem this way. Okay. How? Well, we need a key point which we will not be able to prove. This requires some development of what is called flatness. Okay. For every finitely generated R module, M, the graded Betti numbers of its initial module, okay, which is just, initial module was this, the submodule of the one that the initial terms of the Grosvenor basis generates, is bigger than or equal to beta ij of M. Okay. So this needs a way to be able to move from M to in M in some controlled fashion, in which you can compare the free resolutions, the ranks of the free modules in the free resolution. Okay, so this is well beyond our scope now. So, okay, but there is such a result. So with this we can actually reduce to, so now reduce to monomial, reduce meaning reduce a proof of, reduce the proof of Hilbert-Syzygy theorem to modules, to monomial submodules of M, monomial submodules. Okay, this is okay. So, but what do they look like? They look like I times EI, where F has basis ER. So this is basis of F. Okay, but this direct sum as direct sum of modules, and it is not very difficult to check that if you take minimal resolution of each one of the components, their direct sum of the complexes will give a direct resolution of the free resolution of the direct sum. So therefore, further we reduce to monomial ideals to each component of this, and then this is just something dummy. You can just treat, just have to prove for II. Okay. So, okay. So we want to show that for a monomial ideal I inside R, I has a minimal free resolution of length less than or equal to n. N is the number of variables. Okay. In fact, I mean, there are explicit description of what a free resolution would be. It need not be minimal, but at least we can prove this statement from that. Okay. So this is not, I mean, there are concrete descriptions of non-minimal free resolutions, or more correctly, not necessarily minimal free resolutions of length less than n. So definitely a minimal resolution will have length less than n. So one can prove this, but I would like to do it in a slightly different way, which will motivate us to for the next lecture. So if I is not prime, let's ask. So I monomial ideal. When will I be a prime? Well, if it involves if a minimal generating set involves an actual monomial, meaning a monomial of degree at least 2, then it cannot be prime, because it would be something of the form some xi, xj, xk. But if that, in that case, either xi or xj or xk has to be inside here. So is a prime ideal if and only if I is generated by something of the form some xi1 through some xic, 1 less than or equal to I1 less than to IC less than or equal to n. It is generated by a bunch of variables, the subset of the variables. Okay. So this is only when it's prime. So if I is not prime, okay, if I is not prime, choose a variable xi not inside I, and xi not inside I, and xi divides monomial minimal generator of I. Okay, such thing will exist. Okay. Then check that I colon xi, so this will be an exercise, intersect, so this will be strictly bigger than I, and I plus xi, this will also be strictly bigger than I, is equal to I. So this we will do as an exercise. Okay. So now we have an exact sequence 0 to r mod I colon xi. This we have done earlier. R mod I to R mod I plus xi to 0. So this is great degree preserving. An element of homogeneous element here goes to a homogeneous, its residue class of same degree here. So this is degree preserving. In order to make this degree preserving, the 1 bar here has to go to xi. So in order to make this degree preserving, the generator here has to be in degree 1. So now this is degree preserving. Okay, so now there is a standard construction in homological algebra, okay, called Kozsul lemma, which you will work out as an exercise. If you have a resolution like this, okay, and say G0, G1 and so on, one can construct a resolution for the middle term by taking F0 direct sum G0, appropriate maps. Maps are not obvious. I mean, one can work it out, but they're not, maps are not just direct sums, and so on. Okay, so with appropriate maps. So this will be in the exercises to figure out what the maps should be. Okay, and okay, so one can, and there's more. There's actually, which we'll see later, what is called a map of complexes, which we will see in the next lecture. But there is such a thing. So in other words, if this has length less than or equal to n, and this has length less than or equal to n, this also has length less than or equal to n. Okay. So therefore, okay, we can, so if you choose I to be maximal where it's not less than or equal to n, by Noetherian, these two things have less than or equal to n. Okay, so by Noetherian property, okay, we may assume the result for I colon x and xi and I plus xi by Kozsul lemma it's also true for I. Okay. So this this argument worked precisely because it's not prime. So now, therefore, we can assume it is prime. Okay. So now we have to handle the prime case. So therefore, may assume I is prime. Okay. So let's take a couple of examples, and this will be resolved. This will be done using what is called Kozsul complex. So let's say I is x1. So this is, for now it is just an example. Okay, we will do this properly in the next lecture. So then here's what we could do. We could take I, we could take r minus 1. This is multiplication by x1. It has to be injective. I mean, it will be injective. This is the domain, and then 0. Okay, this is the resolution for one variable. If you have two variables, okay, then the resolution is this basis element multiplies by x1 and this basis element multiplies by x2 is multiplied by x2, and here, so the kernel of this one can verify again that so I'll explain the shift here, but the kernel here, again, the same idea, r1 e1 plus r2 e2 equals 0 means r1 x1 plus r2 x2 is 0. The x2 and x1 are irreducible elements, not multiples of each other. So then x1 has to divide r2 and x2 has to divide r1, and then we would get this. Okay. It is the same argument that we did in the earlier example, in the previous lecture. Okay, so this is it's a free resolution, two variables. these are examples of what is called Kozsul complexes. So in the next lecture, we will look at Kozsul complexes, try to understand the construction behind them. Again, it will require some detour into homological techniques. You could use this as a motivation to study more homological algebra. Okay. So this is the end of this lecture.